I'm Jenny, and I hope to teach you a little bit about activation energy and the effect of temperature on reaction rates. So I will show you guys a couple examples from Chem 1A that you might remember, relating Hess's law and the Born-Haber cycle with lattice energy. You'll see how this relates to activation energy at the end. Okay, so I will admit, when I originally picked this section, I did think that this had more to do with the elevation change that relates with cooking times and why you need to increase your cooking time at higher elevation. This isn't quite true, so let me try to phrase it a little bit differently. So say you're cooking, let's say you're baking, and what changes is the activation energy is how much energy it's going to take for those molecules or those ingredients to combine to become the product at completion. So you want to enjoy your cake, but you don't necessarily want to eat it raw. An example of Hess's law. This is from chapter 7, talking about the enthalpy of an exothermic reaction. We see that the change of the enthalpy goes up before it goes down and settling to be the product. The potential energy in the internal energy of the system is stored in chemical bonds. These bonds are released and new bonds are formed, making the products. When we look at the combustion of methane, we can see the same trend occurs. The enthalpy increases before the formation of carbon dioxide and products form, but that product formation is also releasing heat. So that's why we see the negative enthalpy of the reaction here. So you might be asking yourself, what exactly is the activation energy? It's the energy needed for the reaction to take place. So you have to think of it kind of like you need to make it over the hump on a roller coaster before you can enjoy the ride of the product, the end result. These molecules have to collide with enough energy. If you add heat, it speeds this reaction up. When they reach that activation energy transition state, they have the highest energy from that collision. That's that activation energy difference, and that's what we're measuring. You can think of this also as when the temperature increases, the molecules are more likely to interact with each other at a faster speed. Let me bring you back to another example. This was from chapter 10. So instead of calculating the enthalpy, the change from the reactants to the products, we're kind of going the opposite direction, and we're going from the reactants to that transition state. This example shows a way to calculate the lattice energy of an ionic solid, showing how sodium and chloride break apart before they form one solid. Page 653 in the textbook, just using an example, 15.7, the decomposition of ozone. Alright, so I'm going to show you how to make one of the Arrhenius plot graphs. This is using Google Sheets. So if your numbers don't turn out right, I'm going to just say this at the beginning, then you can select your numbers and you can format number, and then if you go all the way to the bottom, it'll say more formats, and you can custom number format, or you can go right here, it says scientific, but if you want to have more significant figures, then you might want to go to this one, and then this is where you would put in, how many decimal points you'd want in your answer. And this type of number is going to be scientific notation, so it would say E for your 10 times the. All right, and so then you hit apply. So that's already on my table here, but I'm going to show you how to do this yourself. So you'd put your starting number. In our case, you're going up by 100 with each temperature. So what we would do to save time, you can input this as an equation and just do an equal sign, and you can do the number right above it and say plus 100. You gotta select the number. You drag this corner down and it's gonna fill out all the numbers for you. So I've done that already. Go ahead and give it a try on your own Google Sheet. Next, input your rate constants. These are just taken from the given information on page 653 in the textbook. But this time we're doing 1 over the temperature. The rate is in Kelvin. So you just do, I'll do an example down here as well. So you just do the equal sign, say 1 divided by, and then you'll select the box. So you'll say the temperature. I'll show you my example down here. Corresponds to this box. And then you just hit enter or return. Select the corner and just drag it down. That's going to fill out the same equation for all of these corresponding numbers. The next column you want to fill out is the natural log of the rate constant. Again, you'll do your equal sign. This time you have to type it in. The natural log is going to be ln. You do have to do the parentheses, otherwise this will not work. And then select the value. So then our rate constant here, you would select that one and parentheses and then hit enter. This does have a suggested autofill, so you can always try that. I'm using Mac, so it's suggesting command enter. Next, you just take these 2 columns, your temperature and your natural log. You can select over here, insert the chart, or right up top, insert, select chart, and it's going to give you the options here. Hit customize on over here. It'll come up say series. You'll want to make sure that you add the trend line. It's linear. Show the r² value and label it with the equation. This is the most important part. You're using this equation. Now that we have our equation from doing the graph work, we got to remember that our slope is equal to our lowercase k, or our constant. We plug this in for the equation of activation energy over R, the gas constant, because gas is in our chemical equation. Multiply both sides by R. That gives you the value 93.1 kilojoules per mole is our activation energy. We do round this to 3 significant figures because that's what our starting data table gave us. Next, we're going to take the given information of 2 rate constants at different temperatures and put them in for the 2-point form of the Arrhenius equation. Using the natural log of the rate constants and the given information at the temperatures, we're able to get the activation energy for this equation. Now go ahead and pause the video and try to predict the rate constant if the temperature was 525 Kelvin. We can predict the rate constant for the new temperature by using the activation energy that we found in the previous example. We can use the Arrhenius 2-point form equation to solve for our rate constant. We can also check our answer by plugging it back in, solving for our activation energy. Did you get the same answer?